So our answer is, when the source was a cosine 2 pi f naught t, the output is also a sine wave of the same frequency, but with a different phase and a different amplitude. Very nice. And it turns out that result is quite general. So let's review again how we found it. It's so important, I really want to make sure we get this down. So the source was a sinusoid. I thought about it as the real part. I know by converting to impedances that this is the way the amplitude of the output is related to the amplitude of the source. And over here, that is Vn, right? Because that's the amplitude of that complex exponential. We now know that the output can be written as the real part, where you put in how the circuit transformed the voltage amplitudes, and just finding the real part, just like using the procedure we did, converting to polar form gives us our final answer. Looks a little complicated, but we'll understand what this means in just a second. We'll have a clearer interpretation of it. Now, let's handle a little bit more general case. Suppose there was a phase. The source had a phase. Well, the way that works out is now Vn is a e to the j phi. So it really is a complex number now. Using impedances, we're always going to find that the complex amplitude of the output is equal to something, whatever the circuit does, times the complex amplitude of the source. This something it does is called a transfer function. And if you look back over what we've done, it always depends on frequency. So that's why I had to put the frequency of the source, f naught. And I'm just going to define that to be V out over Vn. In general, it's the ratio of the complex amplitude of the output divided by the complex amplitude of the source. This captures, the transfer function captures what the circuit does to the amplitude and what it does to the phase. So here's what's going on. We found using impedances that that's the transfer function in Cartesian form, and as we've seen, it's much easier to deal with mathematically if we convert that to polar form. This is routinely what we do for any circuit. Use the impedances, we're going to wind up with a result in Cartesian form. We then have to do some calculations to figure out what it is in polar form, and then it gets very easy to figure out what the output is. So when the input is that, the output is always this for any circuit containing resistors, capacitors, and inductors. That's always the answer. This is very, very general. So we now can see that assuming the source was a complex exponential actually had a big payoff because the circuit was linear. Now, I'm going to point out some mathematical details that are very important, and that is, suppose we had a sine wave, real sine. Okay. Well, the easiest way to think about sine is as the imaginary part of something. Well, everything goes through. The superposition still goes through because of Euler's formula, and you also use imaginary part. And this is very important. So however you define the source as being related to a complex exponential, either by an imaginary part or a real part, you use the same representation for the output. So when the input is that, the output is this. And that's, again, a general result. You can use either the real part or imaginary part, whichever one is easier. I'm going to point out that you can actually work this the hard way, if you will. You can assume a cosine is the imaginary part of something. Notice the presence of this because of the phase shift by pi over 2. You can represent the sine as the real part of something if you want to. You should actually go back over our little example, RC circuit example, once you try using the imaginary part and see if you get the same answer we got using the real part. except you have to change the amplitude of the source by e to the j power 2. You better get the same answer once you simplify things, and trust me, you will. Okay, so here's the big picture. For any circuit we have, pretend the circuit is a complex exponential over there, although it really isn't. Use impedances to find the transfer function. Now we express the source as the real part or imaginary part of a complex exponential. This works for sinusoidal sources. And the output is going to be the real part or the imaginary part, whichever one we assumed. You can try to switch them. Of the transfer function times the complex exponential of the source. That's the procedure using impedances to solve any circuit that has a sinusoidal source. So let's go through this for an example. You ought to try something a bit more interesting than an RC circuit. And what I'm showing you here is what's known as an RLC circuit. So our circuit now has a capacitor, a resistor, and an inductor. The source is this, and I'm going to ask you two questions. I want to find the transfer function. I want to find the output for this input. Okay, so we now know what to do. So here we go. So the first thing we do is we take our circuit and replace it by one having impedances, where again these are complex amplitudes. Now, I've done a little notational thing for you here. The impedance of this 1 farad capacitor is 1 over J 2 pi F. Well, to simplify the mathematics, the manipulation of these formulas, as you're going to see in a second, it gets pretty complicated. I like to think of J 2 pi F as a single variable S. And I write the impedance that way as just being of the capacitors being 1 over S. What I'm going to do is use current divider, voltage divider, all those tools, and then at the end replace S by J 2 pi F. So the impedance of a 1 farad capacitor is 1 over S. The impedance of our 2 ohm resistor is still 2. And the impedance of our 4 Henry inductor is 4S. Okay, so we now want to find V out. Okay, so the complex amplitude V out is pretty clear that this is a parallel combination in series with that impedance. So I use voltage divider, and I find that V out over Vn is equal to 2 in parallel with 4S divided by 2 in parallel with 4S plus 1 over S. Okay, so now we multiply everything out. We get 8S over 2 plus 4S divided by 8S over 2 plus 4S plus 1 over S. Bet you didn't know that electrical engineers have to be very fluent with fractions. This turns out to be one of the things that happens all the time. You can see now why I did not want to write J 2 pi F everywhere, because it's complicated enough as it is. This happens all the time, like I said. All right. So we can do some things to simplify this. The first thing is notice that this ratio has some 2's in it we can cancel. I can make that a 4, make that a 1, make that a 2, make that a 4, 1, and a 2. And now we can simplify this. So I'm going to multiply top and bottom by S, okay, to get rid of that. That puts an S squared there, oops, squared, and puts a squared there. And I'm going to multiply top and bottom by 1 plus 2S, which gets rid of it down there and up there, and this becomes 1 plus 2S. Okay, So